Hello everyone. Today we will learn about a special case of planar motion called projectile motion. We will learn about equation of motion of a projectile, equation of path and range of the projectile. We will start with the definition of a projectile. A projectile is an object moving in a vertical plane with initial velocity v0 and at an angle theta 0 from the horizontal direction. Thus, the initial velocity of the projectile is a vector quantity having magnitude v0 and the direction given by angle theta 0 from the horizontal direction. The motion of the projectile is such that acceleration only acts in the vertical direction. Acceleration only acts in the vertical direction. And this acceleration is due to gravity only. This is called free fall acceleration. The movement of the projectile is similar to what is shown in this figure. The projectile is launched at an angle relative to the horizontal direction. The projectile moves upward and then it falls down. During this movement, it travels a horizontal distance also. The projectile is launched at an initial velocity v0 and at an angle theta 0 from the horizontal direction. The x component of the velocity is v0x and the y component of the initial velocity is v0y. We can write vector v0 in terms of its components as v0 equals to v0xi plus v0yj. Now, since theta 0 is measured from the horizontal axis, we can write v0x as v0 cos theta 0 and v0y as v0 sin theta 0. The goal of this lecture is to analyze projectile motion using tools described in the previous videos. We will assume that air has no effect on the motion of the projectile. Now, one important aspect of the projectile motion is that the horizontal and vertical component of motions are independent of each other. This means that a factor affecting the motion in one direction only will not affect the motion in another direction. We can verify this by performing simple experiment. We can take two balls. One ball we can drop vertically downward and the second ball we can shoot it horizontally like this. Then we will find that at each instant of time both the balls will be at the same vertical height and they will reach the ground at the same time. Thus, if t1 is the time taken to reach the ground by the first ball and t2 is the time taken by the second ball to reach the ground, then we will find that t1 is equal to t2. Now, in the context of the projectile motion, what this means is that we can take components of velocity, we can take components of the initial velocity in a projectile motion and analyze them separately. Now, in a projectile, horizontal component of the velocity is same as there is no acceleration. This means that the horizontal component of the velocity doesn't change with the position of the projectile. The acceleration acts in the vertical direction. Therefore, we will find that the vertical component of the velocity changes with time. When the projectile is moving upwards, we will find that the vertical component of the velocity is reducing and at the maximum height the vertical component is 0. And when the projectile is coming down, we will find that the vertical component of the velocity is increasing in the negative direction and it is maximum just before hitting the ground. Now it is clear that the horizontal component and the vertical component of the motion are independent of each other. We can analyze them separately using our knowledge of motion in a line. So first we will analyze horizontal motion. this, there is no acceleration in the horizontal direction. The horizontal component of the velocity doesn't change, and the position of the projectile in the horizontal direction changes according to x minus x0 equal to v0x times t, where x0 is the initial x position of the projectile. Now v0x is the x component of the initial velocity, and this is equal to v0 cos theta 0. Therefore x minus x0 is equal to v0 cos theta 0 times t. We will label this equation as equation number 1. In the vertical direction, gravity acts, therefore the position of the projectile changes with time. The velocity component in the y direction also changes with time. The position of the projectile with time can be obtained from this equation: y minus y0 is equal to v0y t minus half gt square. Y0 is the initial y component of the position of the projectile, and v0y is the y component of the initial velocity. Now v0y is equal to v0 sine theta 0. Therefore y minus y0 is equal to v0 sine theta 0 times t minus half gt square. We will label this equation as equation number 2. The velocity in the y direction changes with time according to the relation Vy equal to V0y minus gt. Now again putting V0y equal to V0 sine theta 0, we get Vy is equal to V0 sine theta 0 minus gt. We will label this equation as equation number 3. Similarly, we can find the relation between the y component of velocity and the position in y direction by using the relation Vy square is equal to V0y square minus 2gy minus y0. Putting the value of V0y, this becomes Vy square is equal to V0 sine theta 0 minus V0 sine theta 0 square minus 2gy minus y0. We will label this equation as equation number 4. Together, these four equations completely define the projectile motion. So these four equations can be used to obtain any desired values of the position and the velocity of the projectile during its motion. Now that we have determined the relations for locating the projectile at different times, we can use them to determine the equation of the path that the projectile takes. We will do this by eliminating time from equation 1 and equation 2. For simplicity, we will assume x0 and y0 equal to 0. Now we have the equation 1 as x equal to v0 cos theta 0 times t, and from this we can obtain time equal to x by v0 cos theta 0. And from equation 2 we can write y is equal to v0 sine theta 0 times t minus half gt square. Putting the value of t from this equation to this equation, we obtain y is equal to v0 sine theta 0 times x by v0 cos theta 0 minus half g x by v0 cos theta 0 square. We can cancel v0 and v0 here, and we know that sine theta 0 by cos theta 0 is tan theta 0. Therefore y is equal to x tan theta 0 minus gx square by 2v0 square cos square theta 0. This is the well-known equation of a parabola. Thus, the projectile takes the path of the parabola during its motion. Next, we determine the range of the projectile. Now, the range of the projectile is defined as the horizontal distance traveled by the projectile when it reaches the initial height. To determine the range of the projectile, we simply put x minus x0 as r and y minus y0 as 0 as the projectile reaches its initial height. Thus, from equation 1, we obtain x minus x0 equals to r, and this is equal to v0 cos theta 0 times t. From this, we obtain t is equal to r by v0 cos theta 0. And from equation 2 we obtain y minus y0, which is equal to 0, and this is equal to v0 sine theta 0 times t minus half gt square. Putting the value of t from here into this equation, we obtain v0 sine theta 0 times r by v0 cos theta 0 equal to half gr square divided by v0 square cos square theta 0. Here we have rearranged the equation and move this equal to sign here. Now we can cancel v0 and v0 here. We can cancel one of the r's here, and we can cancel one of the cos theta 0, and we can obtain r equal to v0 square by g2 sine theta 0 cos theta 0. Now we know that 2 sine theta 0 cos theta 0 is equal to sine 2 theta 0. Therefore, range r is equal to v0 square by g sine 2 theta 0. Now the range is maximum when sine 2 theta is 1. Therefore, r max is equal to v0 square by g, and this occurs at 2 theta 0 is equal to 90 degrees or theta 0 equal to 45 degrees. Thus, when a projectile is launched at an initial angle of 45 degrees, the range of the projectile is maximum. If we plot the projectiles at different launch angles, we will find these graphs. This graph is for theta 0 equal to 30 degrees. This orange graph is for theta 0 equal to 45 degrees, and we see that this is the maximum one. This green graph is for theta 0 is equal to 60 degrees, and this red one is for theta 0 is equal to 75 degrees. Thus we see that range is maximum when the launch angle is 45 degrees. In a similar way, we can find the height that the projectile reaches during its motion. We know that at the maximum height, y component of the velocity is 0. Therefore, to determine the height, we simply put vy equal to 0 and y minus y0 equal to h in equation number 4. Now equation number 4 is vy square is equal to v0 sine theta 0 square minus 2gy minus y0. We put vy equal to 0 and we put y minus y0 equal to h in this equation, and we obtain v0 square sine square theta 0 equal to 2gh. From this we obtain h equal to v0 square sine square theta 0 divided by 2g. This is the equation for the height of the projectile launched at speed v0 and at an angle theta 0 from the horizontal direction. Now we know that range is maximum when theta 0 is equal to 45 degrees. Therefore, to determine height of the projectile, when range is maximum, we put theta 0 equal to 45 here. Now we know that sine 45 is 1 by root 2. Therefore, h when r is equal to r max is equal to v0 square into 1 by root 2 square divided by 2g, and this becomes equal to v0 square by 4g. So this is the relation for h when r is equal to r max. We can also find the time of the flight of the projectile. We realize that at maximum height Vy equal to 0, therefore putting Vy equal to 0 in this equation, we obtain 0 equal to V0 sine theta 0 minus gt, and from this we obtain t is equal to V0 sine theta 0 divided by g. This is the time taken by the projectile to reach the maximum height. The time taken by the projectile to reach the maximum height is equal to the time taken by the projectile to drop from the maximum height to the ground when the initial and final heights are same. Therefore, time of flight is twice of this, and therefore TF, that is time of flight TF, is equal to 2 times V0 sine theta 0 divided by G. This is the equation for the time of flight of the projectile launched at velocity v0 and at an angle theta 0. That's all for today. In the next video, we will take some examples on projectile motion.